Okay, machine by vision by machine and vision by the brain. And let's work together during this lecture and beyond, yeah? And recall that we start with our new framework, we say, because vision has been kind of the old brother in the neuroscience field where, you know, people study audition, auditory systems, so they all like to copy vision. But nevertheless, we should not feel comfortable too much because we kind of haven't been not making progress as quickly beyond V1 as we did before V1, yeah? And so therefore, this motivates, say, have we been asking the wrong question about what vision is? And one thing we dug out is that we really have to see vision with selection as in the center stage, that we have an attentional bottleneck. And this bottleneck is starting as early as V1. And that's probably the reason why we cannot make progress beyond V1 in the same way as we did before V1, yeah? And so, for instance, in before V1, you can just map the receptive field. That means you map the filters by just trying out reverse correlation and so forth. But beyond V1, that doesn't work so well. If the information is not passed to these neurons, you cannot do reverse correlation to measure receptive field so easily, yeah? Okay, so here I just list lots of things, a lot of things, a lot of question marks and so on and so forth. It's more like, hey, what is the counterpart in machine vision? Let's talk about it. So for instance, you know, human vision has the bottleneck and machine vision doesn't or does, yeah? And vision really is looking and seeing. The looking is really the selection bit where you want to delete and not delete. A looking bit is, and in machine vision, maybe this is segmentation and classification, yeah? Looking, segmenting foreground, background, and classification. And we can see that in human vision, we have non-random looking could happen before seeing, but could segmentation occur before classification? We can ask that question. Central versus peripheral vision, do we have that? Well, maybe we do, right? Maybe not. It depends on your implementation, your particular application. There's no reason why we can't if we need to. And we have this feed-forward, recurrent, and feedback. In what form are they existing in current machine vision? I love to discuss with them what visual illusions are they similar in, and you know, visual understanding. In fact, in a sense, like maybe I shouldn't have turned off the recording because this is really part of the lecture. So let's just have fun, yeah? Okay, start with attentional bottleneck, and we can see that, you know, again, this is for those of you who have seen multiple times, let's enjoy one more, but some of you is new, yeah? Can you tell the difference between these two images? Because you have attentional bottleneck, you cannot see all the details, then it's difficult if you haven't seen that before. It's the airplane engine, so therefore it shows that with one single example, we are blind almost to everything, and turns out that our bottleneck is so big that we throw away more than 99% of information in our retina by the time, yeah. And looking and seeing, okay, so let me show you that looking and seeing are indeed two different processes, okay? So normally in our human brain, our vision process, they happen so quickly together that you think they're the same thing. Looking and seeing, in Chinese, we call 看见, yeah? It's actually the one word. But anyway, looking and seeing. Imagine you want to see this uniquely oriented bar. It's very quick, but somehow you add horizontal vertical bar, it just can't see it so easily, yeah? But if it's just because this X shape look the same as that shape, but this is skinny X, so you don't get so confused, okay? But anyway, now I want to show you that I have this particular example to separate the looking and seeing for you. I'm going to show you this image like that, but it's whole screen like that image. I want to tell you, please look for a uniquely oriented bar, okay, like that. It could be anywhere in the image. Ignore horizontal and vertical bars, trying to turn your clever brain off. What do you mean by clever brain? Because in your V1, all you have is orientation. Your V1 doesn't see this letter X. This letter X is IT, okay? So try to be as stupid as your V1, then you can do it. That's why when you chase after a fly, the fly can just always evade you because they're not as clever as we are, PhDs, yeah? But anyway, try to look for that, okay? Ready, steady, go, ready, yeah? Okay, ready, steady, go. Where is it? 1 second, 2 seconds, 3 seconds. If you see it, raise your hand. 2 people, 4 or 3 people. Okay, you are all too clever. Yeah, you have to kind of, but anyway, that's where it is. Oh, more people start to see it. So after 5 seconds, only a minority of people have seen it. Okay. But remember, if you remember my visual saliency hypothesis, that V1 actually see it right away because this is very salient, uniquely oriented bar. Yeah, is that really true? Okay. So usually in an experiment, we show people this whole computer screen start with a blank screen with a dot in the middle. Yeah, they have to stare at the dot. When we're eye tracking, see that eye is in the middle, then we see this. And so their gaze start in the middle, then we can track their eye and see where they go to. Okay. They go first gaze like that. No training needed. V1 is so clever. Okay, so on average, after 1 second, 50% of them already the gaze is within that range. After 2 seconds, 90% of the trials gaze. So for you, after 5 seconds, most of you haven't seen it. Why? Actual gaze have already reached there. And then, okay, just first of all, go back. Okay, this is looking. That means you segment without classify. Your V1 jump, mainly by bottom-up sensing. Okay, just let me go back. Put your gaze here. Can you see that? You can't. No cheating. Put your gaze. Do you see that's different? No. Remember crowding? Remember I showed you the letter T? If it's crowded by the surrounding letter, you would not be able to see it. So with crowded so many things, you don't see it. However, your V1 does not need seeing, it will lead you there by bottom-up saliency. That's why no training needed, you can do that. Okay, for all subjects, they do that. Okay, within 2 seconds, 90% of trial, their gaze went in there, and that's it. Okay, after the gaze went in there, now this is in your central visual field. Originally, when you start here, this is in your peripheral. Now it's your central visual. Suddenly, you realize it's letter T. But actually, I did not ask you to look for letter T. Remember, I asked you to turn off your brain about vertical, horizontal, but just look for uniquely oriented tilted bar, right? But somehow you just can't help it. You see this letter X, then, okay, you hesitate. This is red is the trace of your gaze continue following. Okay, you first of all hesitate, then you say, must be not. You keep going on, go somewhere else, and then you come back. Yeah, this is amazing. Okay, the idea is you start by your gaze start here. Okay, so your gaze start here, and you fly over there with blue trace. That's a looking, and then once you stay there, you start see it. Okay, looking finished, you see it, and then you do decision making. You veto it. You say, it's not. It's not, and then you go like that. Okay, so this looking, seeing in this case is pitted against each other. That's why you can tell the difference. But in normal life, you're looking, literally, you're seeing so naturally that you may not realize it's two separate processes. Yeah, that's very, okay, that's the C. And so therefore, looking and seeing, we see that is this segmentation, classification, I don't know. But non-random looking can happen before seeing. Okay, segmentation, can it occur before classification? Because this is the example where you're looking occurred before you see anything distinctive in there, right? Okay, so goes like that. It's non-random. You just usually the first gaze go there, second gaze go there. That's the usual situation. In machine vision, maybe you just randomly until you hit it. No, so far is it the case? If you don't have a top down or whatever, okay, this is actually against your top down. You just go over there. Okay. And you also think, how much is your top down? So this is our human brain, and this is in the front, this is in the back. Usually front is associated with the smart part of the brain. It's really big. It's called frontal areas. This black bit. In chimp, it's this big, like that. And dog, smaller. Cat, it gets smaller, yeah. And of course, these are all mammals. Mouse is even smaller. So therefore, our smart part gets smaller. But our back is always there. So let me show you bottom-up looking, or even in a little frog can do it. How do you? Oh, I'm sorry. Somehow this is not the. I'm sorry. Yeah, but anyway, gee, I thought it was a video. Well, I should, but anyway, this is so bad. But anyway, to this segmentation. You can segment these two, but if you classify this as a texture, that is a texture, they are the same, yeah? Okay, so this is an example that we human can do segmentation without classification. Because if a flexor they're the same, you say, oh, this is A, this is B, therefore this is a boundary. You can't do that, no? Okay, so this is an example. In fact, there's saliency, you can do that, okay? Central versus peripheral vision in what form? I don't know. In many applications, but let's see central versus peripheral vision. And we again notice that in our retina, cone receptor density versus eccentricity from the central fovea. Yeah, central fovea is 0 degrees, and to the left and right over all the way to 90 degrees. And the cone really is really packed in the central fovea, immediately just decay. It's like really, we look at the world through the tunnel vision of really just there, okay? And the density as a function of eccentricity E is like that, with this parameter E0 really small, yeah? And this is how we are going like that. And this is how you can intuitively see central peripheral vision. Peripheral, you need letters so big before you can see it. And central, if you set your gaze in the center, very small letter you can also see, yeah? And this is again, for those of you who have never seen it, you know, you can fixate here. And the periphery, even though you have low spatial resolution, you can still see the 2-letter T's if you fixate here, okay? Just fixate here. That means the resolution, sampling resolution is still good enough. However, if you suddenly put more letter crowding it, suddenly you don't see this letter T anymore. So it is beyond your retina for this to happen. This is your central limit in the brain, yeah? Just as long as you don't cheat. Of course, if you move your gaze here, you can see it, no problem. So obviously, this is an algorithmic level in your central brain, yeah? So, yeah. And here we see that peripheral vision is for looking and central vision is for seeing. Peripheral vision for you to look, and then once your gaze is there, you start see. And so therefore, central and peripheral vision may be a separating functions. One is for segmentation, yeah, and the other is for classification, maybe. Looking and seeing. Feed-forward, recurrent, and feedback processes. Many reciprocal connections in the brain, as I mentioned, that in this diagram where we have retina, LGN, V1, V2, V3, V4, VP, and a lot of these connecting lines, I don't have an arrow to it. So here I have an arrow. That means this is just feed forward. But here, LGN to V1 is less than V1 to LGN feedback. This feedback is massive, okay? Yeah. And V1, V2 also feedback quite massive, although I forgot which one is more. And all of these, I don't have these arrows. That means they are both feed forward feedback. They are really reciprocal in the brain. And this random dot stereogram, I believe, is a function that likely involving feed forward and recurrent process, and perhaps also feedback, because our gaze perhaps, okay, here, just show you. This is a random dot. We add a square in front of it, well, just on top of it, but because they have the same statistics, you can't see the boundary. Okay, you copy it to another eye, so this is in the left eye, this is in the right eye, they're exactly the same. Okay, the square, I just highlighted it for you again. And if you shift the square a little bit in one eye, and remove the border again, you again cannot see them if you don't fuse them together in your brain. But if you fuse them together in your brain, your two retinas send the signal to your brain, then you fuse it, then you can see the square in front of you by binocular disparity. This, I believe, involves both feed forward and recurrent, and perhaps feedback, because your gaze, once you see it, we're going to kind of zoom in, a little bit like active vision, you know, you kind of put your camera to a little bit zooming in there, yeah, and so like that. And here is quite vividly feedback, maybe in a way, I'm not sure whether it's also, well, vividly recurrent, because somehow, I'm not sure how easy it is for you to turn off. It's so automatic, yeah? And this is, again, actually don't take my word as truth, because I'm actually guessing. And so I think, oh, it must be this. It's must. I'm not just. This is kind of a last lecture of today. I like to just kind of a thinking loud with you, or to share. Oh, yeah. Mm-hmm.
I wonder how far you can take this example that you've seen triangles many times. There's a very good trial for that. To change it to higher and higher degree volume. At some point, does it work?
Do you like to come to the microphone? Maybe other people can also hear it. Yeah. And also, I find it very difficult. So.
That was
with the arm. Maybe this is what it is. Okay, just maybe speak a bit louder. Yeah.
So I was just saying that this effect.
Yeah.
How far can you take it? In the sense that triangles, we know that triangles, we are very familiar with triangles.
Yeah.
Very good trials for triangles. Is it true that if you change this to higher size polygons?
You may not do that. So here are some other examples. This is another thing. I think it's recurrent, but later on we'll have a duck. Have you seen a duck?
Yeah.
Okay, so maybe duck is not the same as triangle.
So,
yeah.
So I guess my question was that was that really an example of recurrent processes, or is it an example of highly set processes?
I think this is a recurrent process, but it's a guess. Okay. Because this is something related to something called border ownership in V2. This is something maybe related to that. And that's a recurrent network in V2. As you can imagine, now we have this recurrent network in V1. The next thing really is quite, yeah. Sometimes people talk about mid-level vision, but I'm not sure. Yeah, that's why I kind of guessing out with you. Yeah. Yeah. And so duck will be slightly different from that. Yeah. So you can say, well, once that, yeah. Okay, very good. Thank you. Okay, so this I feel like it may be something border ownership signal to that as well. In my first lecture, we talked about like illusory contours and border ownership. Maybe I was a little bit too slow, so therefore I skipped it a little bit quickly. But if you like, it's actually in some of the videos for the first lecture. You can go back and find this border ownership thing. And this might be connected with it. The idea is here is a border, and this border is owned by this black area. Okay, so in biology, there's something called border ownership. You find V2 cells tuned to it. And it's a pity that we know so much about V1 and we know so little about V2. So this is one of those frontiers that we haven't quite really comprehend. And of course, knowledge about V1 has driven a lot towards the CNN development, which is really copy after V1 without including a lot of these V2. Of course, before we really understand V2, we don't know how to incorporate it. But so that's why this is kind of a thinking loud with you, yeah? Here is the example that you cannot turn it off, no? What is it? Yeah? This is again, occlusion and border ownership, these kind of things. Yeah. So is this really a recurrent within the brain area or feed-forward feedback between brain areas? Yeah. And this, I imagine it's feedback, but yeah. For those of you who have not seen it, what is in this image? Yeah. And we just need a little bit of hint. And after the hint, you can see this duck really vividly, yeah? And looks like as if it's qualitatively different nature as this and that. So I'm using the word looks like. What do you think? What do you think? You are trying to ask, yeah?
That example, once you see it, kind of stays in.
Yeah, yeah. But do you think they are the same nature as this triangle? Because triangle, I don't need to hint to you. You just see it right away. Or is it because it's too simple? I don't know.
Just because we know triangle is so well, like the triangle is so strong that you can like instantly see the triangle. So if the shape
Mhm.
same thing, the same color.
Yeah, certainly the fact that this is a one line is a very simplistic low parameter region, yeah? And so therefore you require very little parameter, while the duck requires a bit more parameter to describe. And so maybe, yeah, this is what you mean by being simple. And we're so familiar with it. Yeah, I guess there's a point to that. Because triangle is very what? So by IT, all the neurons, most neurons have resistive field quite big, 20 degrees or 50 degrees, okay? So a thumb is 1 degree. So 20 degree is like, this is 10 degrees. So when I look at you, your face is only 2 degrees, yeah? You are, yeah, I can cover you with 2 thumbs. Yeah, and so therefore, a duck and these triangles, they are well within one single resistive field of an IT neuron. Yeah, of course, they're not really within one single resistive field of a V1 neuron. So, yeah. Yeah, this is quite interesting. Yeah. Possible, yeah, indeed, there's so many parameters. On the other hand, yeah, you're right. I mean, maybe it's just a matter of quantitative parameter. You can say, okay, here's a hint actually. How many parameters can I do this hint with? 1, 2, 3, 4, like 10 parameters enough? Something, yeah. Of course, the triangle only needs 3 parameters. So well, 3 or 4 parameters, yeah. So interesting. But you can say that once you see it, the duck is maybe slightly less vivid than triangle. Yeah. And response latencies, as I said, you know, this is at 40 millisecond. Why? Yeah, 70 millisecond. It's quite a long gap, because you imagine maybe 10 millisecond from V2 to V1 to V2, another 10 millisecond, yeah, could be 30 millisecond longer. And then it's 100 millisecond. This is as fast as you can, yeah, for a very fast pilot, you can already start to push a button. And I mentioned, some of you already heard it, that by 125 millisecond after the stimulus onset, you can decode from 300 IT neurons to categorize object into 8 categories quite successfully. Yeah, and so this is, of course, you say, okay, you can decode from these IT neurons, but how did these 300 neurons reach their firing rate in this way? There must be an underlying algorithm. We don't know the algorithm, that still doesn't count. Just because you can decode, you can read out, that doesn't mean we know the algorithm, yeah? Somehow, but nevertheless, it seemed to suggest that this is a feed-forward algorithm, maybe, because these are the kind of objects that CNN can also decode, they can also recognize. However, for objects that CNN find it difficult to decode, then you need a bit longer time. You have to wait a bit longer, 25 millisecond longer, and then you can also read it out. Then again, what is the algorithm? Yeah, this is a kind of a, yeah, recurrent processing. This is a kind of an evidence or suggestion for recurrent processing for the harder ones. And things like when things are very noisy in your input, noisy images or occluded input. Yeah, so for instance, if I cover my face with hand, you can still see my face. Yeah. And it's occurrence in human, we don't have some big problems. But somehow maybe you have problems. Okay, in this case, this is occluded letter B's, yeah. Okay. And these occlusions or things are among these noisy or ambiguous inputs are among these harder objects where the animal vision can do and feed-forward network find it more difficult. Yeah, and this is the case where I show the top-down feedback. For those of you who are in the last lecture, you were already heard it, but bear with me. I show this to people who are new to here. So imagine you put this left and right eye image, this for the left eye, this for the right eye, using a stereo goggle to let them see it. They are designed in such a way that if you add it together, it's actually stripes tilted clockwise from horizontal. And if you subtract them from each other, it's stripes tilted anti-clockwise for horizontal. They are the same contrast. They're designed in such a way, yeah? And then you can ask observer, what do they see? They tilt this tilt or that tilt. And turns out that when they ask what they see, if they have to force to answer, they will have 2/3 of time. This is probability, the time that they report this tilt. Is 2/3 of time they report this tilt. This is only 1/3 of time. That means twice as likely they will say they see this tilt rather than that tilt. Okay, even though they have the same contrast. So the idea is, this is a very clear case of feedback. Well, it's a very case of supporting the feedback idea. The idea is this signal is passed to higher visual areas to tell that, hey, it's this tilt, tilt number 1 versus tilt number 2. And when it's tilt number 1, the higher brain area say, gee, I'm not sure because I also hear another voice. So if you are right or the other one is right, who knows? So it has this internal model of the world start thinking and say, wait a minute, if I perceive this, it means that this image must show it to my left eye and show my right eye. Okay, that's what I expect. In the world, if I see something, must my left eye. Of course, the best way is to go all the way to the retina and check. Go all the way to the left retina and check. But there's no feedback all the way to the retina. So the easiest way to do is actually just go to V1 and check with the summation, because summation would represent the average between the left and right eyes, yeah? In V1, the representation is summation and difference. So go check with it. So I say, okay, if it's tilted to this way, then let me reconstruct the input which could be to the V1 and check and say, oh yeah, agree. Happy, tick. But same thing, this voice saying tilt the other way, they'll go check, but it will check according to its internal expectation of the world, that I think this signal should be in a summation channel. So when it go check and say, oh, summation channel didn't say that. And so therefore this signal is vetoed. And once you do that, this signal will have a higher weight. And this going back to check is analysis by synthesis, meaning that we're trying to analyze the feed-forward signal by synthesizing what the actual original signal should be and check with the origin. Yeah. Now there is an assumption that as if by higher visual areas, it does not know that this comes from this channel. Okay, because if it knows this comes from this channel, it will go back and check with this channel, right? Why does it go check with that channel? The reason is starting from V1, the information starts to be lost. It didn't tell the higher brain area this signal comes from this channel. It only tells the brain area, higher brain area, partial information about the tilt. But it did not say this tilt number 1 comes from the ocular summation channel and tilt number 2 comes from ocular difference channel. It's just trying to be frugal and saving and not telling all the information. Yeah, that's the bottleneck of attentional selection. Turns out that you can also train human beings. You say, is it trainable? Can I train human beings doing learning to learn which input comes in? Okay, I actually did that. It cost me more than a year and it's a failed experiment, so I never published, but I will share with you. So what I do is I make myself, where it was a stereoglass, or actually it was a mirror stereogram, and I show something to my left eye, show something to the right eye, and I have to guess, is it to my left eye or right eye without blinking? Huh? Of course I can cheat by blink one eye, but I don't. Okay, then I say, okay, it's left eye. Then I say, you're right. It's a left eye, you're wrong. So it gives me feedback. So I'm trying to do supervised learning to train myself, yeah? And I'm trying to see whether I can train myself to learn it. I can't learn it. until I hit a stage where my eye movement is getting involved. So I don't know what's the answer. Yeah, I don't know. So therefore, it's never published. But it is also known by other researchers that they could not do that either. So therefore, I was just trying to try it out myself. You know, sometimes you read papers, you're not sure what they actually did. You might as well try yourself. And of course, which students like to do this experiment? Nobody. So therefore, I do it because I try it. What happens is I learn. After three weeks, suddenly I could do it. Gee, I can tell whether it's from the left and right. What happened? And then I realized that I have astigmatism. Yeah, you know, astigmatism. So one, I have a slight difference, and this difference is so tiny that I was not aware. And so somehow, with enough learning, that my brain picked up this signal. Yeah. And I go, oh my God. And so therefore I have to remove that. Once I remove that artifact, I again cannot tell whether it's from the left or right. And then I try myself again, another 3 months, and suddenly I can see again. Now what? And I discover another artifact. And so therefore this goes on for 1 year. But nevertheless, it's very interesting. Somehow there is this hard bottleneck in V1. I just refuse to send certain information forward such that I cannot even train myself. So that's very weird. But anyway, with this, then you have to get feedback when you have doubts about the visual input, and this feedback will carry your top-down bias about the world. When bottom-up not send this enough information there, it will have to use its bias. Yeah, so that's the idea. And yeah, we call that feed-forward, feedback, verify, and reweight, FFVW. Reweight means two equally weighted hypothesis non-zero weighted after verification. Yeah, so this is weighted more highly. And in periphery vision, you don't have that strong bias, so that shows that feedback is mainly in central vision. So that shows the central peripheral difference. Yeah, feed-forward, recurrent. And then what are the forms of feed-forward, recurrent, and feedback in machine vision? I'd like to hear from you. What are the current form of feed-forward, recurrent, and feedback processing? Yes?
When you do the whole thing, then on top of the other one, it takes a little bit time or the something, and well, it's not the per se feedback, but if you get the conflict and multiply it, then it's pretty much the same as if you pass processing information, because model control will maybe get on there up to
Sure, so it's query for more information. And you know what your query for.
I mean, it's still a like
Yeah.
but at least that's like
It's quite successful, yeah? Or the limitation.
I think it is. Well, like when I was okay. No idea about it.
Yeah. Why do you need to know this?
So I think most of your pictures do have some work model thinking.
The last example is we talk about bottom. So there is kind of a tension of bottom.
Yeah. So for input speech, for example, versus segmentation, and doing segmentation like without the bottom part. And I think it's quite the whole system some for
Well, in this case, it's very interesting, as if, you know, there is kind of a bottleneck. Yeah, because we motivate the difference between central peripheral vision by a bottleneck because of the eye movements. And because of bottleneck, that's why you need feedback to query for more information. This is query is, yeah. Could you be a bit louder?
I think out of these points, you have all, like most of them involve their vision machines and right. So you do get attention
So how do you define attention?
oh, you have a mechanism called attention.
So what do you define the mechanism for attention?
So you have systems that are made to focus on a certain part of your image, text, or what you have. So you basically make this part for consideration.
Take this part in consideration.
It sort of gives saliency maps between patches of an image. So the patches kind of can attend to one another.
Speaking of the bottleneck, like the kind of default factors in autoencoder, where the point is that you want to be able to compress the image to some small space and
You want to do some small, say it again, a bit louder.
you take your original image and you want to use a network to convert it into a small data. And from the small vector, you want to be able to construct.
Okay.
That's like a pretty common to generate. So that's I think less used now.
Well, UNet is quite like that, but then it has those connections that go across.
But there's definitely a lot of other working at the bottom like try to force something. But and it works well. You can reconstruct it in a small variable. So yeah, I agree that a lot of these things are present in some subfield.
So that's for representation learning, right? You're talking about, are you talking about this autoencoder kind of thing? Yeah.
Yeah.
And that's not, this is in order to train a representation, while that kind of feedbacks in the particular
Yes. No.
object recognition algorithm. Is that right? So are they the same or no?
Yeah, there are different ideas, but you older before learn how to smart use it all like and then how to extract.
Yeah, but that actually is data compression rather than attention. Attention actually deletes something. To foster a bottleneck, you actually do not delete it because it will fully reconstruct. So that's actually data compression. While here, the visual system actually has deletion. They lose information, otherwise you will not notice the difference. Yeah? So that's slightly different. No?
Like the
Yeah. That's right.
And actually, there is work done on using data sets that for segmentation. They have put reconstruction loss on the area inside of the segmentation. So the idea is that we want to be constructing the object itself and not.
Okay.
So there's also like related work on
So you want to reconstruct the object.
So the idea is that yeah, we're getting this whole scheme, but the loss is only applied to whatever is inside of the segmentation aspect of the model. So if you really
But
want
then you only segment it, and then inside you fully have to reconstruct.
so what the model is encouraged to do is reconstruct what's inside of the segmentation aspect, and not reconstruct all of it. So it can lose all the information from it. So in this case, it's less, a little bit less. And it's more compression than only for the important areas.
But within that area, actually, is fully non-loss. Right?
Yes, so that's where it's really hard to get. It's usually on the data sets.
Yeah, so one of those things I actually also want to really learn the latest of these. So perhaps I should go to those kind of workshops and yeah, and then talk to you afterwards. Talk to these workshops and the tutorials to hear what's very And this is the thing that we kind of already started discussing during our break. Illusions. Yeah, we see these illusions. Are they similar in machine vision? Yeah. Okay, this illusion maybe I'm not sure. Maybe it should not really. I actually don't know what this illusion is. Yeah.
I was just thinking about the illusion of the adversarial images, right?
Yeah, uh-huh.
And it looks like a given. And I remember seeing a couple of years back a paper that demonstrated that, in fact, those adversarial perturbations, although they don't look salient to you or me, they do contain sort of like textural information that is predictive of the class in the original data set. So perhaps if you've given this panda a little bit given shaped fur or something like that, that you wouldn't see an actual image of a panda, but it gets totally lost, I guess, from our visual stream in the bottlenecking. But nonetheless, it is predictive of the class. It could help machine algorithm achieve superhuman performance for like fine grained classification because of not having that bottleneck. Even though it seems counterintuitive that it's giving the wrong answer of something clearly looking like a panda, calling it a given, but maybe if you got an image like that off of a camera sensor, maybe it is a weird looking given. You know, pandas don't have fur that's quite that.
Yeah, but the reality is that we can never have a panda that looks like that. With that adversarial perturbation. In nature, if you ever saw that, it probably is actually good. So the adversarial examples aren't necessarily bad, but
Yeah, although you would imagine this particular texture is actually related to the particular data set in training the panda and gibbon, yeah. And so you wonder why is this training algorithm in the end that the result of learning is on some superficial detail that maybe another algorithm may not have it, but maybe yeah, it is something say yeah.
If it's in the data, then you know.
Yeah.
We don't notice it, but it may be
yeah.
predictive of the class.
Yeah, interesting. So if we say, you know, these are the type of things that based on V1. Well, this actually, I don't know whether it's based on V1. All we notice is this is happening in the peripheral vision, doesn't happen in central vision. And this, there is evidence, some suggestion that this is the V1 motion signal, actually related to our eye movements. We have a small jittering eye movement called some motion signal, yeah. And yeah, and the one that Adelson illusion, I don't know. This is obviously what we can understand just from the last lecture. And this, where does this come from? In the peripheral vision, I can't even see it. Okay, try to look away. Can you see it? You just feel eyes going away. It's difficult, huh? But somehow this is in the central visual field. What is that? Yeah.
It's the color constancy, right? Or
A little bit like color constancy, yeah. On the other hand, you know, the shadow from the cylinder seem to matter, but you can also block the cylinder, but you can infer the cylinder's existence. You can still see it. Okay. You don't need cylinder there.
still you infer the illumination.
Yeah, you infer there is something standing there casting the shadow. Yeah, you don't need to actually see the cylinder. But on the other hand, the color constant usually is talking about like a uniform illuminant from the sky or something, but this is a small local patch of shadow. Say it again.
How I understand the illusion that I imagine so I see the shadow. So I imagine that originally this block is lighter because it appears this color under the shadow. And I'm guessing that there is actually no shadow on that side, which is why it can be the same color, but I imagine it is like originally white. You know, that's what's happening.
Yes. Do you imagine, you see the way you talk about it is so intellectual, but when we see it, it's so automatic. We don't use so much intellectual reasoning, do we? Interesting. But maybe we do. We don't realize. I mean, this is funny. You know, therefore, as I say, there's so many things we don't know because kind of when I see this is brighter than that, I'm not thinking shadows and this kind of stuff, huh? So yeah. Yeah.
So if you want to describe you make the bar.
Two bars or like that one?
Yeah. Yes.
Yeah.
Yes.
Mhm.
In this one, I'm curious. So a very particular thing with the brain or with intelligence that I find is that we are algorithm makers. We can think of an algorithm to make. How do we know that on the next example, on page 8, what we do is automatic? Because, for example, the implementation we have this template matching thing. We have the template and we try to find this person here. How do we know that when you tell us, yeah, look for this on the next slide, we don't think, okay, now our brain doesn't think now I will search for a thing inside there. We have a visual similarity thing that we can detect basis, and we don't find it inside data. How do we know that it's not that's not an intelligence and something that is really second order thinking? Why do we think that this is like something that is low level?
I do not think it's so low level. It's just somehow then low level. Maybe it's in V1, but it's actually quite intelligent. What do you mean by low level? In the sense that I wasn't aware that I was thinking about it.
Before what you tell us do this task, it's not that we look at the scene and we do this task. You ask us to think of this, to find it.
Well, I asked you to look for a uniquely tilted bar, and I asked you don't pay attention to the vertical bar and horizontal bar.
Yes, but we already set the task. It's not about attention, we pay attention to it.
No, I do not completely follow what you're trying to say. Say it again.
It's like you ask us to do the performance of the task, and then we think of an algorithm, a way to search this.
Yeah.
And so I feel that this person should have some kind of intelligence, and we have to think of this algorithm at that point, which is that we search the screen, we have already visual matching, we can understand the vertical and the horizontal with the corner detectors that we have. But in fact, it may be really intelligent the fact that we find that because we actually have to think of this algorithm. But we think that's really fast. Even computer vision, in fact, and by matching, we can find it really fast. But I don't know.
Yeah.
Similar examples without the task, and it would still be doing pretty immediately focus on one simple was core.
Okay. Then that is enough.
Okay.
Yeah, it's very low. Well, it's from
Here you're doing what?
What's the speed that it takes for the eye to know the auto stack?
200 milliseconds. Well, actually, it's quite slow. Usually 300 milliseconds. For this kind of a very busy scene, you were about 300 or 400 milliseconds. Yeah. But if it's just one dot, it can be 200 milliseconds.
Like in the previous slide there on second, is there ever a situation where
Seldom. That's a very puzzling thing that we are seldom. Let's say you have a blank screen, and then you suddenly flash something, ask the subject to just go to wherever it flashed. You can almost 250, yeah. But nevertheless, V1 is already firing at 40 milliseconds. So why does it take such a long time? I don't know. Yeah, this is very puzzling. Was another thing in superior colliculus is an ancient structure. You see, V1 go to superior colliculus and move the eye. Superior colliculus has many layers. And turns out that from the top layer to the bottom layer takes a long time. And we do not understand why. Like a 50 millisecond just spent on superior colliculus. Very strange, yeah. Say it again? It's a very small region. In monkey, it becomes a very small region. Yeah, this is, see, here is this. See, this little thing is really tiny. Yeah, in fish, this bit is kind of half the brain. Of course, Fish's brain is very slow. Yeah, so it's really. And so the V1 in comparison to this, the whole cortex, sometimes you wonder why, the brain is such a strange design that our eyes are in the front, the V1 is the back. It's going to go such a long distance, just go there. Why?
Is it myelinated?
Yeah, part of the way is myelinated, the optic nerve is myelinated. But the thing is, why is it such a long distance? When I think about it, in ancient time, we don't have such a brain cell in the middle. This neocortex is new, it's kind of squeezed, none of wiring is committed to it. You cannot put the eye in the back, the eye has to be in the front. And so it's like if somebody, let's say the eye is connected to superior gaze, they're very close, then somebody squeeze the middle, and the squeeze the middle goes so big.
Is the SC area white matter or gray matter? I guess it's midbrain, right?
Midbrain, yeah. It's many layers.
Of very tiny neurons.
Very tiny neurons, and those neurons are kind of doing very unimportant things in primates, but they're doing much more important things in lower animals. So if you go to my webpage, I have a comparative review of across species, how birds and fish and primates say. So it looks like as V1 grow bigger and bigger, relatively superior gets smaller and smaller, as if they start to trade off. Yeah, so it's very funny. So if you lesion V1, the monkey cannot make eye movement for 2 months. But if you do that lesion V1 in mice, the mice wake up. No problem. So therefore, superior cortex is still doing main functions. Yeah, and so therefore you can see the algorithm is changing as evolution changed the circuit. It's very. So sometimes you think, okay, there must be some kind of commonness across species, so you may want to. But anyway, what is this illusion? I have no idea. Does the machine make these kind of illusions? Yeah. Oh, that's true. It's not an illusion. But anyway, you may not call it illusion. Yeah. It's actually reality. You're right. Yeah. You're right. I should not mix this illusion. It's unlike this. You're right. You're right. See, that's good. You're all paying attention. You say, this is not illusion. Very good. Yeah. You were going to say something, Jonathan?
Yeah, basically.
Same thing. Very good. Okay.
Why would the brain have the
Yeah.
useful
Yeah.
for life when like in the same way?
Yeah.
There's a lot of sense in
Yeah.
concepts, but then really.
Yes, the brain is being very clever to have that. It's not illusion. Very good.
Why would you expect it to make that?
That's right. That's right. Yeah.
Brain never runs.
Uh-huh. Uh-huh.
Even in deep learning, it kind of sometimes makes sense to look of output distribution data or failure cases to understand but I'm not sure whether common cases of this kind of patterns are always the best way to understand how we perceive the world, because these are in a way output distribution. We've never seen such an example in our lives. It's kind of constructed.
Yeah, but just because we don't see it in our life, it's not a reason not to use it to debug. Sometimes you debug, always go to the asymptote to debug your program, okay? We are scientists trying to use it as a tool, and sometimes you want to use the ensemble average to study a particular property or something, but sometimes you want to choose special values, just like if you're Gaussian function, I want to choose exactly center value that has a special meaning to us for me to debug a program, trying to say whether the program is this way or that way. And there's indeed argument where you have to use natural scenes and whatever. These depend on the question you ask. Yeah, sometimes we actually want extreme cases. Now imagine Isaac Newton trying to test his law of gravity on Earth. That would be horrible. He has to go extraterrestrial to do that. Why? It's not really natural, but that's where there's no friction, that you can actually have the theory to the pure sense. And so in a sense that there's maybe this is the situation where maybe in engineering, you want robustness or in situation that most of the time it works. In science, we're trying to discover algorithms, and in such cases, we use asymptote as a very diagnostic tool to say what is the, imagine I use a MATLAB program and somebody say, how you do Fourier transform. I can write my own code to a Fourier transform. I can use toolbox from MATLAB program for transform. But if the first time I use toolbox, I don't know how to use it. I will just test it on a few known examples of Fourier transform, see how it works. Okay, the known example are always extreme cases because they are very indicative. Yeah. And so therefore, often in these kind of illusions, we actually search for special cases, even though maybe that's the different cases compared to the other scientific question when you say, what is the ensemble average? Yeah, sometimes we use ensemble average, sometimes we don't. And such as Isaac Newton needs to use extraterrestrial example to test his law of gravity. He doesn't test it by a projectile or something thrown into the atmosphere and see how it orbits, yeah, or how it falls down through the leaves and all this. He doesn't do that. That make sense?
I don't think disagree with it needs to. I need to elaborate more, but I need another.
Okay, sure. It's okay. We are just. We don't, we are just talking completely thinking together, yeah? We don't really know the answer, we just talk, yeah? And this is kind of, this is what I like about the last lecture, we just talk, yeah? So I like to hear what you say, yeah.
I have a point to add to the attention topic that we talked before, because if you talk how attention might be significant, but I think there's things that are also quite different, right? So in the attention mechanism, which you might not be attention really human being, it's usually bottom-up attention, but it's the previous layer within an attention map for what they look in the current year. But in human vision, it's top-down attention. So you're looking at these features and then you're saying, oh, I need to look at this part patch really one, go back again, and we infer where I have to go. This different kind of attention, where feedback and attention seem to go hand in hand. Human vision compared to the attention channels we have in the
Okay, so here is when the attention, when it's people may be saying different things. One, attention means you select a fraction of information. The other is when you go back and look at something, is actually a decoding process. It's hypothesis testing. Now, would you call this hypothesis testing attention or not? Often in psychology, people call it attention. But then this attention, this label is applied to different situations and different things, and that cause lots of but this is, so this is why I feel like to separate things into encoding selection. I don't even use the word attention, but actually selection is part of what psychology call attention. So selection with data selection, selection this data and not that data. And then decoding, in decoding, part of it is feed forward and part of it is hypothesis testing verification. And this verification coming back, would you call that attention? Yeah, and of course in psychology, people say this is attention. And so therefore, I think just to bring attention, this is attention, bring our scientists' attention back to them and realize that they are different things, and maybe just to think about maybe different things might help, yeah. And so when this case about attention, okay, maybe deep layers is a layer I suggests to I plus one something. You call that attention in machine learning?
Yeah, that's what
it's called attention. So therefore, that's yet something else. Yeah, you can, yeah. And then of course, I feel maybe it'd be nice we can all put our attention candidates there, and then we sort it out, and then we can kind of re-terminology that might be helpful. I don't think any term is necessarily better or worse, but to kind of come to a particular turn that we can all talk together might be helpful. Just like the scientific community have to come up with a metric system. Okay, agree. One kilogram is this. That's it. Okay, we all agree, and then we can talk. Yeah, it might be helpful. You know, these kind of exchanges is very good. Yeah. So yeah, and so this is illusion, and then we come to the, I say, whether the machine and a human might have illusion. Pain, maybe noticing it might also as a root of making connection between the machine. Yeah, this is the something I talk about. Okay, anyway, and therefore we can call the visual illusion in human as an adversary attack in human vision. We can call it that way. Yeah, because after all, it is illusion to us, and therefore thinking that machine vision is imitating human peripheral vision. And then the visual understanding, and here our understanding is more or less a definition. We say that the reason you don't get food is because you have a generative model in feedback. And then can we define it as visual understanding? That if you understand, then you can generate. Yeah, that's kind of a definition. And if we agree with it, then does the machine don't have visual understanding? Well, if it can generate, it could also do it. Can it do well? Well, we human don't do always best. Yeah. Say it again. I just define understanding as the ability to generate. Okay, that's definition. You can define another way. So therefore, in a sense that again, we need agreement between us. Shall we? Let's define understanding as ability to generate. In our current lecture, we are defining that way. That if you can generate, say, oh, I think it should come from 2i, blah, 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 then I generate this would be input, then come to verify. That's the definition of visual understanding. Yeah. We can also discuss maybe another way of definition of visual understanding and then apply it to, okay, say understanding category 1, understanding category 2, and then articulate it out might be useful. Yeah, to do it. Does that make sense? Yeah. So, and then of course, people talk about, is the machine vision understandable? Well, machine vision understandable. What is understanding? You know, in a sense that we are defeating ourselves, you know, our understanding is questioning our vision. Our vision sees this impossible object. Our understanding tells us this is impossible. I just like to close on a note that we are quite far, but nevertheless, it is a fascinating route to kind of discover, and maybe this discovery can happen together with engineering, invention. So I kind of call science as discovery, engineering as invention, but we are probably at a root where discovery and invention can have a lot of exchange to do with each other, where, yeah. So this is going to be fun, and I'd love to, yeah, adversary attack some. And so, is machine vision understandable by humans? And by this, I like to feel that it should be, even if it's not yet. Because in the end, I suppose there should be, and I hope it to be, there's kind of a one intelligence that is common. It's just principle. In practice can be many different applications, implementations, whether it's implemented in silicon or implemented in neurons, it's just different hardware. Yeah, and so therefore, if we can understand in such a degree that I understand how the calculator works, so I use it. And I have no doubt whatever it tells me. And that kind of understanding, hopefully, we get.